So in this video, in this section, we're going to be looking at some comparison tests we can use for convergence and divergence for different series, and then I'm going to introduce you to the limit comparison test. So here, what a comparison test means is if we can find a series that's similar to the series we're trying to figure out whether it converges or not. If we have one that's similar and the one that we're trying to compare it to, or the one we're trying to figure out converges, if the one that is similar is always greater than or equal to that function for all k, then we can say that if that one that we know converges, then the one we're trying to find out about converges. So again, we have to look for those conditions first in order to be able to use that. So you'll notice that this is very similar to a geometric series where we have k equals 1 to infinity 1 over 2 to the k. And the reason I know that is because here 1 over k to the k, we have 1 over 2 squared, 3 cubed, 4 blah 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 blah. This one is different because it's always 2 to a power. But for the conditions, when we have 2 to a power, we know that that is always going to be bigger than the rest of these here. So then the series itself will be bigger. All these numbers are going to be bigger, and so the sum itself will be bigger if it converges. So we can use this one because it's the sum is going to be bigger than that one. So our R for this series is 1/2, and this converges. So since that one converges, this one here also must converge. So again, we have to show the conditions are met to use the comparison test for it, but then we can use this particular series to compare. Now, you're probably thinking, how the heck did you know to use the 1 over 2k? And you're trying to find a series that you know converges and that will be bigger, the sum will be bigger than the sum you're trying to test for whether it converges or diverges. And so this was an easy one. We knew that that geometric series converged because our R was 1 over 2. We can also use P series where the P is greater than 1, because those are ones that we can quickly find out that they converge, and then we compare them. But again, you're just going to have to practice on picking the right one for comparison. So for divergence, you want to do the opposite. You want to find a series that is smaller, that the sum is going to be smaller than the one that you're trying to compare it to. And if that one diverges, then you know that the one you're trying to figure out has to also diverge. So in this one, what we can do is we can say that we know that n plus 3 over n plus 2 is greater than 1. And n plus 3 over n times n plus 2 is the same thing as 1 over n times n plus 3 over n plus 2. And so that is going to be greater than 1 over n. So if I choose c sub k to be 1 over k, then I know that c sub k is smaller than a sub k. That's what I just figured out right here, that this is smaller than this. So then I can use this, which is the harmonic series, which I know diverges, and therefore I can say that this also diverges. And now we have what's called the limit comparison test. And so we can look at the limits as n approaches infinity in the ratio of a to b. So we've got the one we're trying to figure out whether it converges or not, and then we have one that we're comparing it to. So what we do is we make a ratio of those two. And if the limit as n approaches infinity for those two is a number, then whatever this series does, this series will also do. So if this series that we know converges, then we know the one we're trying to figure out also converges. If it diverges, then we know the one that we're trying to figure out also diverges. If the limit is equal to 0, so if it was a number but that number is bigger than 0, then we have this condition. If the ratio is equal to 0, and we know that this converges, then we know that the one we're trying to find also converges. And if the limit is infinity, if this one diverges, then we know the other one also diverges. So this looks very similar to the one that we did in the example right before, where we had k plus 3 over k times k plus 2. But if we try to use the same technique with the harmonic series, we don't get the conditions because our c sub k is not smaller than our a sub k. And so we can't use that one. So instead, we'll use this limit comparison test. Again, we'll choose the same ones. So our a sub n is this function with the n's. And we're choosing our b sub n to be 1 over n. So then we're going to do the ratios of those. So we do the limit as n approaches infinity of a sub n over 1 b sub n, which is 1 over n. Well, that's a complex fraction that we can change to n plus 1 over n. And then instead of dividing by 1 over n, we can multiply by n. So these n's are going to cancel. And then we have the limit as n approaches infinity of n plus 1 over n plus 2. Well, we know that that equals 1. Okay, we could use L'Hopital's rule to show that. So we go back and we get this condition where it equals this a number. This is the harmonic series. And since we know that the harmonic series diverges, then this diverges. So you can see the harmonic series is going to be one that's you're going to use as a comparison. Geometric series you'll use as a comparison because you can easily figure out if that converges or diverges. P series you're going to use as a comparison because you can also easily figure out if that converges or diverges. And so this limit comparison test can be very helpful. So this is another one where we can use the limit comparison test and we can use a p-series in this case to see to be our comparison. So what we want to do is we want to figure out, well, what happens to this function as n gets really big? So we can change this function by factoring out of the bottom that n to the 3/2 power, and we get this piece. And the limit as n approaches infinity for this piece right here is 0. So for very large n, we have this 1 over 3 n to the 3 halves times 1 over 2. This part goes away. And that gives us this p series here. Because this is just a constant multiple rule for this. This is a p series where p is going to be 3 halves. So our a sub n is 1 over 2n to the 3 halves plus 5, and our b sub n is 1 over n to the 3 halves for our p series. So we do our ratio. And again, we can end up multiplying by the reciprocal. So that gives us the limit as n approaches infinity of n over n to the 3 halves over 2n to the 3 halves plus 5. So once again, we get that case where we can factor out that n to the 3 halves. So just like we talked about up here, we end up with this limit right here. And we said that that equaled 1/2. And so because that equals 1/2, that is a number between 0 and infinity. So because the p series, since p is greater than 1, the p series converges. And so then this series also converges. So this is another one where we evaluated at some very large n. So again, we're going to do some algebra where we factor out some roots here. Get this, and so we're approximately to this. So for very large n, this will go to 0, and so we're getting 0 there. And again, we can use this harmonic series, and we know harmonic series diverges. So when we do that limit comparison test with the harmonic series, a sub n is this thing. And b sub n is our 1 over n. Okay, so remember, you're taking these and you're evaluating them at very large n to see what kind of series they're close to. This one happened to be close to the harmonic series. So now we do the limit test with the ratio. Okay, that's the same thing as multiplying by n. So if I just multiply the top through by n, this is n to the 1/2, and we add 1/2 and 1 to get 3 halves. So we get 3n to the 3 halves on the top, and then this thing on the bottom. Well, you can see in here, this is n to the 3 halves also. So then we know that that limit is going to be 3 over 1, or 3. Again, that's a positive real number. So because the harmonic series diverges, we can say this also diverges because we got that number that's a positive real number. And on this last one, we're going to use a geometric series. So we can see that this geometric series, because of this plus 5, is very much like this, which would give us this, which would be a geometric series where r is 2/3. And so because r is less than 1, that series converges. So our a sub n is this, and our b sub n is our geometric series. So our ratio is going to be that, or 2 to the n over 3 to the n. If we multiply by the reciprocal, the 2 to the n's cancel out. And then we have 3 to the n over 3 to the n plus 5. So once again, we have that just plus 5 thing. That's going to equal 1. So if you remember that, again, that goes in our between 0 and infinity, a positive real number. And so since this one converged, this one is also going to converge. So in each of those, we had a different kind of series where we could determine whether they converged or diverged, and we use that as our comparison. And when we did our limit comparison test, we always got a number that was a positive real number. And so then we were able to determine that it did whatever the one we were comparing to it did. So these are different ones that you can compare to. We've got this geometric series where we know it converges if our absolute value of r is less than 1, and if it's greater than or equal to 1, it diverges. We've got the harmonic series, which we know always diverges. We've got the p series, which converges if p is greater than 1 and diverges if it's between 0 and equal to 1. And then we have this series here too that we can compare to, because we know that always converges. So again, we can do those limit tests, and we just have to decide which one we want to compare, which one of these series that we already know whether they converge or diverge, which one we're going to compare to. And then if we make those ratios and we get a real positive real number, then we can say it does the same thing as that series.